Okay guys, welcome to chapter 6. This chapter we are going to be jumping around. We're not going to go in order from the beginning to the end. So we're going to start by looking at some basic indefinite integration rules. So we've looked at a lot of these already. Now you'll notice here with the first one, this is the power rule. Instead of using an x, which we've traditionally done, I'm going to start to use a u, because later on we're going to look at a technique called u substitution, where u represents the inner function. And so I want to get you kind of trained to think about the inner function. So with all of these rules here that I'm about to review with you, you're gonna see a u where you would normally see an x. Okay, so just keep that in mind. So here's our first one. We know that if we have, usually it's x to a power, but here I read it as u to a power. Okay, so n is our power, and you can see that u is our independent variable because of that du on the end. And this is where we said you're just going to add 1 to the power and then divide by that new power, and then we're going to tack on a plus c since we don't have any additional information to find c. Okay, so this was the so-called power rule for integration. Okay, our next one here, if we have u raised to the negative 1, remember if we were to add 1 to that you would get 0, and then you can't divide by 0. So u to the negative 1, of course, is the same as 1 over u to the positive 1, or just 1 over u. So if we were to integrate this, then we're left with the natural log of that inner function. And I'm going to put an absolute value symbol around that because technically it would have to be positive. We know we can't take the natural log of 0 or anything that is negative. So whenever we're using this rule, we want to try to remember to put the absolute value symbol around whatever comes after your natural log. Okay, and here's a quick review of our 6 trig integrals. Guys, the bottom line is you have to just make these flashcards, do what you got to do to just commit them to memory. Look here how I'm again using u to represent the inner function. Again, it's kind of like x, but again, there's a reason behind this which we'll see later on. Alright, u just represents the inside or the inner function, which usually is an x, but not always. So again, there's 6 of them here that you just need to commit to memory. Try to look for patterns. Notice how the negative ones all start with a c. Recall that when we found the derivative of those so-called c functions, cosine, cosecant, cotangent, when we found the derivative of them, you got negatives for your answers. So now, working backwards, we again see those negatives. Okay, so do what you got to do to remember these, get them memorized. Okay, again, there's no formula sheet given to you on your AP exam, so we need to make sure that these are committed to memory. Alright, take a moment and copy these down. Please note that 10 through 12 are BC only. So we saw with number 9, the integral of e to the x, or in this case e to the u, right? Same idea. It's just going to be e to the u. Alright, we get the same thing back. Now, what if the base is not e? What if the base is some other constant which we're calling a? So maybe we're looking at 5 to the x. Okay. So if that's the case, then we have a to the u divided by the natural log of a. So notice how the numerator is the same thing back, and then the denominator is the natural log of the base. Okay. Number 11, if we are integrating the natural log, okay, we end up with the inside u times the natural log of that inside, and then minus the inside. The last one here, if it's not the natural log, now we have the log to another base, which we're calling a. Okay, and this can be rewritten using the change of base formula. Alright, so this is the same as integrating ln of u over ln of a with respect to u. Remember, u is our independent variable. And this rule ends up being u times the natural log of u minus u all over ln of a. So once again, these are just some formulas that you need to commit to memory. Okay? Okay, and finally here we have our inverse trig functions to memorize. So recall that if we were finding the derivative of the inverse sine, this is what we got over here. And if we were finding the derivative of the inverse cosine, we got the same thing as the sine, except it was negated. Okay? These are known as co-functions, If you slap a co in front of the sine, you end up with cosine. So you have this relationship between sine and cosine. So notice how the formulas are the same, except one is negated. Well, this is going to be true with two other pairs. Okay, and here are the final four. So we are looking at inverse tan and inverse cotan. And then we have inverse secant and inverse cosecant. So again, just need to put these on flashcards, commit them to memory. If you are an AB calc person, you are responsible for only knowing these two. Okay, you don't have to worry about the other four. So just the inverse sine and the inverse tangent. Okay, doing my best here to fight through this cold. Hopefully this doesn't sound too horrible. So please bear with me. Alright guys, so we're done looking at specific functions and their corresponding integrals. We're now going to generalize a little bit more, and the first thing we're going to look at is if we have a linear inner function. Now by the inner function I am referring to u, alright, in all of our formulas from before. So what we're going to do is we're still going to apply our rules, our formulas from before, but we're going to take that inside piece, and after we've applied our rule, we're going to multiply by 1 over the derivative of this inside piece. Okay? So here's what it would look like. We're integrating e to the 2x plus 3. The inner function here is 2x plus 3. All right, I'm going to abbreviate this by writing if for inner function. And again, that's kind of like the u that we talked about before. Okay, u is always the inner function. So we know that the outer function in this case is e raised to something. So when we integrate e, we know we're going to get the same thing back. So we're going to have e raised to this 2x plus 3. But then we're going to need to multiply by 1 over the derivative of that inner function. Well, the derivative of 2x plus 3 is just 2. So if it's linear, it's just going to end up being the number in front of x. All right, so then we would end up with plus c. And you could mentally check this. If you were to find the derivative of this answer, you get the same thing back that you see there, and then we would have to chain along a 2, and then that 2 would wipe out that 1/2, and it would leave you with just e to the 2x plus 3. Let's look at another example. Okay, here we go. So this time, notice that the inner function, okay, the inside of what you're given is 3x plus 1, okay? And we're going to call that u, or just if, just to make it clear that that's the inner function. So this 4 that we see in front, recall that one of the properties that we said of integrals is we can take that 4, we can put it out in front of it. In other words, just carry it along. And then from there, we're going to integrate our main function. Well, the main function is sine. When we integrate sine, we said we get negative cosine. So I'll put that negative in front of that 4. Then we're going to have the cosine of this inner function. The inner function always gets carried along, but then we're going to have to reverse the chain rule, is one way of thinking about it. So that's where we said we're going to multiply by 1 over the derivative of that inner function, so that would be 3. So when we clean this up a little bit, we have negative 4 over 3, which can't be reduced, so we'll just leave it at that. And we have all that plus c for our final answer. Okay, next example. Well, notice how this can be rewritten. We can rewrite this by pulling out that 3 up top and back inside our integral, replacing it with a 1 over 6x plus 1. Alright, if you were to multiply that 3 back in, you'd have the same thing that you started with. And this is helpful because we know that if we are integrating 1 over a function, such as 6x plus 1, we're going to end up with a natural log. So, because really what we have here is this quantity is really raised to the first power. And so we're going to end up with 3 times the natural log of this inside piece of 6x plus 1. Alright, now this 6x plus 1 is really our inner function, or the u. And so from there, we notice that it's linear, and so we are going to reverse our chain rule by multiplying by 1 over its derivative, which would be 1 over 6. So that 1 over 6 we can multiply to the 3, reduce, we get 1/2 the natural log. And recall that we said that we could only take the natural log of something that's positive, so we need to slap an absolute value symbol around that 6x plus 1. Then we have our plus c, so this would be our final answer. Okay? And again, I would encourage you to at least mentally find your derivative and then check it. So the derivative of the natural log of that, you would end up with 1 over 6x plus 1. You would be chaining along a 6. That 6 times that 1/2 is how you would then get a 3. So you slide it over, you would be left with the 3 over the 6x plus 1. Okay, and finally here, we are looking to integrate 4 raised to the 2x. So we have a constant raised to a variable power. This is very similar to the e to the x, but we said this was the formula for a to the x. So this one, well, first of all, notice that we have an inner function, all right, which is linear. Okay, so our inner function here is 2x. So our formula for this says that we're going to end up with a fraction, and the numerator is going to be the same thing back. So it's going to be 4 raised to the 2x. Okay, we get the same thing back. The denominator is the natural log of the base. So that's just going to be the natural log 4. And then we're going to need to multiply by 1 over the derivative of that inner function. So it would be 1/2. So there's really nothing you can do to clean this up. You can take, well, I suppose you could rewrite this in a different form. If you were to take this 1/2, put it in front, you have 4 to the 2x all over, all on a 4. If you really wanted to get fancy, if this were multiple choice, this 2 in the bottom would be the same as applying it to the power of this 4. So 4 squared, so 16. So if you really wanted to get fancy, you could express it like that. But again, it all depends if it's multiple choice and what your answer choices are displaying. Okay, so if it's non-multiple choice, we would accept this as your final answer.